So, in this session we will see dynamic programming in action for exact exponential algorithms. Right? You would have seen dynamic programming as an algorithmic paradigm, you would have seen a lot of examples, but here we are going to look at how it is useful in designing exponential algorithms. Okay. So, we will start with the Tsp problem. So, this input has it is a complete graph with distances on the edges. Let us say it is natural numbers. Vertex to vertex is 0, otherwise you have some distance on the edges, and the output, so V is 1 to n. And the output is a permutation such that summation I equal to 1 to so this is I plus 1 mod n. You know what the problem is, you want a permutation such that total length of that cycle is minimized among all possible Hamiltonian cycles in the graph. A Hamiltonian cycle is simply a permutation of 1 to n, and so I want these are the consecutive distances. I am adding the consecutive distances, and that gives me the total distance of the length of the Hamiltonian cycle. Right? When I is n, what is n plus 1? It just comes back to 1. Okay. So, Talzin's assessment problem is a problem where we are trying to find a permutation of the input set of the input vertices such that the total length is minimized. So, a brute force algorithm, so run through all permutations, compute this sum and pick the one which has the smallest, and that gives you the smallest Hamiltonian cycle. So, a running time would be n factorial times n to compute this number, right. So, run through all permutations, and we want to improve this running time. We live in the exponential world, but better exponential running time, okay, using dynamic programming. So, let us see how you would go about doing this, what are the sub problems we want to calculate, and so on, right. So, your Hamiltonian cycle, let us say it starts with vertex 1, 1 must be there in the cycle, and then it may visit any of the other vertices, right. It is complete graph. So, there are all these possibilities. So, the optimum cycle will visit one of this, some j, a neighbor of it is a complete graph. So, some j between 1 and n except 1, j between 2 and n, and then what is the rest of the cycle? Can you just say it in? So, I want to start from j, finish everything else and come back to 1, right. Among all such paths which start from j, visit every other vertex, come back to 1, I want one which finds this would be the minimum such path. Well, how will that path look like? From j it will go to one of its neighbors, and then from that vertex it is going to visit all vertices except I and j, except 1 and j, and come back to 1. So, the sub problem among all such paths, that is going to be the shortest path in terms of the distance. So, sub problem I am going to define is you want to find the shortest distance. So, it is sort of this optimal substructure property I am going to get towards. Start from some vertex j, right. This j would be some such vertex here. Eventually, in this Hamiltonian cycle, the optimum cycle, we will start from j, visit some subset of vertices. That subset is actually 1 minus whatever these vertices, and come back to 1. So, I am going to define this as length of length, distance, cost, whatever. I am going to be interchangeably using this length of the shortest path from J to 1 visiting all vertices of S. So, S would be a subset of 2 to n and it contains J. Okay. So, all I am saying is any optimum Hamiltonian cycle, if I just break up and start from some intermediate vertex and look at the path, then that path must be the length of the shortest path from that vertex to 1 visiting whatever the vertices left are. So, I am going to try all possible subsets. Okay, so, what is my goal? I want to reduce from n factorial to something like 2 power n. N factorial was all permutations, 2 power n is all subsets. So, somehow I am going to get to try all subsets kind of thing, then I will have a 2 power n kind of an algorithm. So, from J to 1, so 1 is some fixed vertex, S is some subset of 2 to n that contains J. These are the sub problems. Okay. Now, in dynamic programming, much of the work is in coming up with what are the sub problems. After that, everything will fall in place. Right. What would be the base case? Suppose S is empty, right? You will go in some incremental order. So, suppose S is empty, then do you know this number? No, watch carefully. Okay, I say J is in S. Okay. So, I want S to contain at least J, right? Suppose S is a singleton set J, then so S is not empty because I want J to be in S. Okay. So, if S is a singleton set, then what is this number? Just read what is it saying, right? Length of the shortest path from J to 1 visiting all vertices of S, but S contains only J. So, I visited it. So, what is that length? dJ1, the length, the direct edge J1, right. So, base case d of J comma singleton J, because this is equal to, what do I call D? Yeah, okay. So, this is exactly dJ1. This is there in your input graph, so you can compute this. Now, at the induction step, right. So, assume that you have computed this for all sets of small size, because okay, yeah. So, assume dJs computed for all vertices J and subsets S contained in 2 to n of size some at most k, k is greater than or equal to 1, because for 1 we have computed it. Now, I want to compute for a larger set, I want to go from D J S, S is of k plus 1 does not matter. So, let us go back to the semantics of DJS. It's length of the shortest path from J to 1 visiting all vertices of S exactly once, right. Visiting all vertices of S exactly once. Why would you visit some vertex more than once? Because you are trying to find shortest path, right. So, I do not even have to put that constraint. Okay. So, this is equal to, I want to start from J, visit all vertices of S and go back to 1. So, can you tell me what it is? How do I go? Yeah. Everything is a neighbor, it is a complete graph, right. So, I go from D J to some I
excluding J
S, start from I, D I S minus J.
and plus Dij and find the minimum of that.
I have that here, DJI, right. So, do it over all minimum of over I. So, I is in S, right, because you want to visit S minus J. So, I want to start from J. So, the semantic says that on the length of the shortest path from J to 1 visiting all vertices of S. So, I will go from J to I and then start from I, visit all vertices of S minus j, go back to 1 and try all possible neighbors. Okay, this is exactly, this can be proved, right, because if you take the any optimum path starts from j visiting every vertex S and goes to 1. If that optimum path goes to some particular I first, then whatever is the remaining must be d I S minus j. Now, this is already computed because it is a smaller sized set. So, you just have to pull it out from here. Okay. And what is my final answer? What do I want? I want a Hamiltonian cycle, right. So, what is my end condition, right? I want to start from, the final answer would be minimum of, I want to start from 1 and go to some I, and then I compute d I v minus 1, right. I want to start from 1. So, this is already computed from my table. So, I finally get my answer like this, is the length of the optimum Hamiltonian cycle. So, this is my nice dynamic programming algorithm. Let us see how much time it takes. So, typically in dynamic programming based algorithms, first thing to see what are the sub problems I want to compute, and that is determined by the structure of the optimum solution. We looked at the optimum solution, we truncated at some point and say that that thing is actually the shortest path from that vertex to 1 visiting some subset. So, that suggests what are the sub problems I need to compute, and then there is a recursive formulation for computing, incrementally computing this sub problems. So, how many sub problems did we compute? So, now to analyze the running time, all you need to do is, so you have a table, dynamic programming table, how many entries are in the table and how much time does it take to compute one entry in the table. You multiply that, you get the overall running time. So, how many entries are in your table? How many entries are we computing, right? We are computing this, all possible j, all possible s. How many are there? 2 power n times n roughly, right, 2 power n minus 1 times n, but roughly 2 power n times n entries are we computing for every vertex j, for every subset s. Number of subsets is 2 power n, number of vertices is n. So, we are computing 2 power n times n entries, and to compute each entry how much time it takes, here it is, right. You want to compute djs, it is a minimum of some entries, and these are all sitting in your table. You just have to add some n different numbers you have to check and pick the minimum. So, that is another n time. So, overall run time will be okay. So, this is an old 70s algorithm due to Held and Karp. So, this is to tell you that even in the exponential world, there are different levels of functions running time possible. So, we can improve it from n factorial to 2 power n square, and this is more or less the best running time for a long time. I think there is a lot of recent work on improving this. Okay. So, for example, we saw in minimum vertex cover case 2 power n was obvious, and we saw some algorithms where you can get to 1.618 power n, and I told you that there are lots of, with just some simple tricks we managed to do it. With some clever tricks we can even improve the base even better. In the case of Hamiltonian cycle, it is harder problem. N factorial is a simple algorithm, and we can improve it to 2 power n square. Okay. So, let us get to the next problem, and what I want to talk about is graph coloring. Chromatic number of G In other words, minimum number of colors you need to color the vertices so that adjacent vertices get different colors. In other words, what is the minimum partition of the vertex set into independent sets, right? Each color class is an independent set. So, you want to partition your vertex set into color classes. Each color class is an independent set, and you want to know what is the minimum number of such parts you can break your graph into. What would be a brute force algorithm for this? So, let's simplify it, and suppose I say is chi of j less than or equal to k. If it's bipartite, you can check polynomial time, but I am asking is it 5 colorable, and so what is what is the try all possibilities algorithm? N power n, k power n. Yeah, if I ask this specific question, that means what? What are you trying? For each vertex, how many choices are there? K colors. If k is the number of colors I want to test, each vertex has k choices. So, k power n. So, I try 1, 1, 1, 1, 1, 2, 2, 2, 2, 1 here, 2 here, and all that. So, each vertex has k choices. So, there are k power n different possibilities. So, once you fix one possibility, you can run through your edges and check whether endpoints get different colors. So, brute force gives you k power n. You want to come up with a dynamic programming algorithm again, right? So, what are the sub problems? So, what you do is just look at the optimum coloring and try and study some properties of it, and that will suggest you what are the sub problems you need to compute. Okay. So, let us say you have fixed one color, some subset of vertices, you have colored them with one color. And if you delete those vertices, then what is left must be an optimum coloring for the remaining graph, right. If there is a smaller number of colors to partition for the remaining, you would have done that and gotten an overall smaller chromatic number, right. So, this suggests what I am going to do is I am going to find optimum coloring for subgraphs, subset of vertices, and I want to look at subgraphs and find optimum coloring, and then gradually build towards optimum coloring for the whole graph. Of course, I have to try, I do not know color class 1, so I have to try all possible color classes. Okay. So, here is a DP based algorithm. So, each color class is independent. So, what I am going to do is write a recursive formulation directly, and you will get an idea. So, I want to claim that chi of g. So, I find one independent set. How do I find it? Look, we are in the exponential world, so no problem, right. So, just try all possible subsets, not a problem. Okay. In the polynomial world, when I say find a maximum independent set, then you should watch how do I find it, because it is NP hard, right. But here I am going to try all possible subsets. So, if I find a subset, an independent set, I am going to color it with one color. Then what do I have to do? Find the chromatic number of the remaining subset and run over all independent sets S of V. It could be as bad as 2 power n subsets, but that is okay. Now, you do not want to do this recursively. Why? Because there are this overlapping sub problems. For some subset, you will find a max coloring G minus S, and another subset they will all have overlap. So, So, what is the way to do? Whenever you have a large kind of number of overlapping subproblems, you do dynamic programming, right, bottom up. So, what are the subproblems we need to compute? This tells you what you have to compute, right. So, you want to compute the subgraphs, find the optimum coloring of all possible subgraphs. So, I will do this in an incremental fashion. So, subproblems would be the induced so chromatic number of the induced subgraph of some x. So, this is induced subgraph of on the vertex set x, right. So, you pick some subset of vertices and I want to find the optimum way of coloring it. How do I do it? I will do it in a bottom up fashion anyway, because that is the problem we are looking at, and we will gradually build towards it. I told you a recursive formulation that told me the subproblems. Now, you just need to do what are the base cases, can I compute them easily, what would be the base case, induce subgraph on vertex set 1, it requires one color. So, that will be the trivial thing, and then once you go to a larger sized subset, you are going to try all possible subsets that if it is independent, I have got to color it 1, if it is not independent, move on to the next set, color it 1 and go to the remaining thing. The remaining thing is sitting in your table, you just have to add it. Okay. This is, I do not want to simulate it in an example, it is going to be. So, basically if you have a graph on some 5 vertices, first I will say try all one element subgraphs. I know I need just one color. Now, I go to 2 element subgraphs, induced subgraphs on that, and I know that I will color an independent, find an independent set there that requires one color, and the remaining coloring is just sitting in your table, compute them. And if it is an empty graph, it requires 0 colors. Okay, so this is the entire algorithm, and eventually you will get the entire vertex. It start from, so base would be g of x, where x is a singleton. Once you get to vertices, 2 elements, 2 vertices, you look at independent sets of those 2 vertices, color them 1, and whatever is the remaining, if it will be a 1 element set or an empty set which you already computed, take it from the table. Now, let us see how much time the whole thing takes, right. And dynamic programming algorithm. So, there are only 2 things you do. How many entries are we computing? How much time does it take to compute 1 entry? You multiply these 2, you get the running time. How many entries are we computing? Here it is, right, the subproblems. So, how many subproblems? For every subset of vertices, I look at the induced subgraph, I am trying to compute the optimum coloring. So, it is 2 power n possible subproblems, right. I am not being very precise here, 2 power n minus 1, maybe because there is no empty subset, you won't look at it and things like that, but in the order of 2 power n subproblems. And how much time does it take to compute each solution, right? Well, this recursive formulation tells you. The recursive formulation tells you, you go to one subproblem, you want to compute the optimum way to color this, here is the formula, right. So, how much time for each of them? 2 power the size of that set. If I give a conservative upper bound, it will be like 2 power n. So, 2 power n into 2 power n, it is 4 power n, right. So, time for each subproblem, so it is 2 power I if, because I am running through all possible subsets and then I am computing, just adding something. This is sitting in my table, this is not a recursive computation. You have to pull out, add these 2 numbers, I am doing minimum. So, it is 2 power I where I is the size of the vertex set. So, if I upper bound it by 2 power n, then this gives you something like 4 power n. which is still better than where we started off with, at least for 5 coloring or 6 coloring, because what was the, we had a k power n. So, if I ask you, can you color the vertex set with 10 colors, the brute force will be 10 power n, but we managed to get to 4 power n. But a tighter analysis tells you it is actually not 4 power n, 3 power n. Why? It is not 2 power n for every subset, right. If your subset size is I, then it is 2 power I, right. If you are working with problems of vertex set of size I, it is actually only 2 power I. How many vertex sets of size I are there in your whole graph? NCI. So, for n choose I problems, it only takes 2 power I, you sum it over all I. What is this number? This is exactly 1 plus 2 whole power n, right, because instead of 2, if you had x, this is the binomial expansion n choose I times x power I, actually x power n minus I, but that is okay, n choose I or n choose n minus I, does not matter. So, this is 3 power n regardless of k for any. So, you want to do k coloring, is the graph k colorable? The simple brute force algorithm gives you k power n, but using this you can improve it to 3 power n. Actually, the same algorithm with a little more tighter analysis you can improve slightly better. How? Because if you come back here, I am not really running over. Okay, so here is one little observation I need to make. At least one color class is a maximal independent set. Take your optimum graph coloring, it is colored partitioned into independent sets. You can easily argue that at least one of the color class is a maximal independent set. How can you argue? Because if it is not maximal, I mean there are some vertices you can add to it to make it independent. Just go find them and add it. Okay, they are all sitting somewhere else. You can find some other vertex, make it maximal. Then nothing changes in the solution. So you give another partition with the same number of, or maybe even smaller. No, but it's an optimum partition, so you won't get something smaller. You get another optimum solution where at least one color class is a maximal independent set. How does that improve my running time? Because if you just go back here, instead of all independent sets of vertex set, I can actually try all maximal independent subsets. Okay. So what? One can prove. So, observation 1, this is a trivial observation. Number of maximal independent sets in any graph is at most 3 power n by 3. It is never 2 power n, it is much less than that. Okay. So, because we are looking at maximal independent set. So, let us suppose a whole graph is a perfect matching. Okay. How many maximal independent sets are there? 2 to the power the cardinality of the matching. What is the cardinality of the matching? N by 2, right. So, if the whole graph is looking like this, perfect matching, how do you get a maximal independent set? You can pick exactly one from each of this matching, right. That will be a maximal independent set. You can't improve it anymore, and there is, you can't even remove anything, because if you don't pick, you can one from a matching edge, you can actually pick. So, that number is at most 2 power n by 2. Okay, so it is not 2 power n, it is like 1.4 power n. What would be an example graph where the number of maximal independent sets is 3 power n by 3? This should give you a clue. The whole graph is a collection of triangles, then the number of maximal independent sets is 3 power n by 3, and you can have 4 clicks. The number of maximal independent sets would be 4 power n by 4, but that number is smaller than this. So, I power n by I, see where it attains its maximum, it will be when I equal to 3. And this is the class of graphs that achieve this maximum thing. So, in any other graph one can show that, I mean this requires a proof. I have just shown you examples of graphs where you can achieve this many maximal independent sets, but one can prove that number of maximal independent sets in any graph on n vertices at most 3 power n by 3. Okay. So, 3 power n by 3 is something like 1.44 power n, because 3 power 1 by 3 is 1.44 something. Okay, so let us come back to our how all of this is improving my algorithm for coloring. We are only running over all possible maximal independent sets of that graph. So, here this won't be 2 power I, this will be, so this number is 3 power n by 3 is the number of maximal independent sets you are running over. So, instead of 2 power I here, you will have 3 power I by 3, which is same as I said some 1.44 power I. So, this will become instead of 2 that number. So, this will become instead of 3 it will be 2.44 power n. Okay. So, even for 3 colorability, 4 colorability is the graph k colorability, independent of k you have an algorithm which is less than 3 power n. And turns out you can actually improve it even to 2 power n using some principle of inclusion exclusion. That is, anybody is interested, that could be actually a nice topic if you want to read and present it next week. I can give you a reference for it, that one can actually improve the running time of this to even better to 2 power n for testing 3 colorability. Okay. So, we saw a range of problems where for vertex cover 2 power n was like immediate and we can improve it to 1.6 kind of thing. Here for graph coloring, getting to 2 power n requires a lot of hard work.